Welcome everybody, welcome to our another lecture in algorithm analysis. In this lecture I will describe briefly about AVL trees. So this is an algorithm analysis course. So AVL trees is a part of actually data structure. So I think our algorithm book does not have enough detail about AVL trees. So if you look into the book, search in the book, you'll see that there are only a section or actually a problem about AVL tree. So if you see the book, okay, first. So what is an AVL tree? So an AVL tree is a binary search tree, okay, that is height balanced. Okay, so that is height balanced. That means we are coming what is called height balanced. Okay, so let us recall that as we discussed in our previous lectures, that where we discussed binary search tree, right? So that we discussed a binary search tree is efficient for searching, especially in logarithm, log with base 2 time, but it may not happen always. It is not guaranteed. For instance, if a binary search tree is built like this way, you see that for like this way is grown is this way, so all the left subtrees are null over here, empty over here, and the tree is grown linearly, right? So the first element comes as 3, then it becomes the root, then next element 5 is greater than 3, so then it will go right side, and so on. And this tree is an imbalanced tree, imbalanced binary search tree. That means its height is n. You can say height is n, right? But for the right side one, it is a balanced BST. Okay, as we see that the data nodes have same data value, but they came in different order, right? So they came in different order. So as we see that for this 7 data value, it may have factorial of 7. Okay, that means many combination of that means arrangement of these values. So there may have many different types of BST with this single data, right? So in that case, it is not confirmed that all BST will be will be balanced like this, right kind, okay, right side. So this is a problem in BST, that it does not guarantee for searching in linear time, in logarithm time. Okay, for instance, for this in the left side, if we want to search for 22, what will happen? We will start from all the way at the beginning, and then we will search all elements one by one, right? So that searching is linear. But whereas in the right for the right tree, okay, if we search for 22, then open we will check with 13. Okay, 22 is greater than 13, then we'll go right side, and then our 22 is greater than 20, so then we will go again right side, right? So then we will find it, and if you do not find it even, then we will need to only 2 searches over here, but here we need actually we need 3 searches over here, 1, 2, and 3, but here we need 6 searches, right? So this is the problem in BST, that it does not guarantee to be searched in logarithm time. So the reason is the problem is that BST does not guarantee to be balanced. Okay, but so AVL tree is a binary search tree that there's height is balanced. Okay, height is balanced. So that means this is the problem of the BST, that its height is not balanced, that problem is solved in AVL tree. Okay, so that means again AVL tree is a kind of binary search tree, but their height is log n. Okay, height is maximum height is big O log n. So then it will help us to do any insertion, remove, and also searching in big O log n time, right? And here with base 2. Okay, so AVL tree is invented by this gentleman. Okay, so I'm not going in depth about this. So the different book has different definition or explanation of AVL tree, but the concept is that okay, the height is self-balanced. Okay, so in so different people explain this in different. For instance, in this slide, either that it says that is node, right? This is the root node, and this is the parent node. This is a child node, and actually these nodes, actually we call these nodes, we call these nodes are leaves nodes, right? So what is the leaves node over here? So this is the leaf node, this is a leaf node, this is a leaf node, and this is a leaf node. Although we know that leaf nodes do not have any child, but they have child. Actually there's a null value, right? This is a null value, or nil, or empty children, right? So actually in some books they say that some authors they say that this has is a height 0, but this slide it says height 1. Whatever is considered, no problem. So if we consider this height is 0, so this is height 0, this height 0, this height 0, this height 0. So then what is the height of this one? This node, we will consider the max branch. Okay, this height will be 1, and then this height will be 1 and 2, this height will be 2, and so for this one is height will be 1. Okay, so redefine it, and then this one's height will be 1, 2, and 3. So instead of 4 we make 3. So in my way, okay, whatever you consider, no problem. But the concept in AVL tree is that it is self-balanced. Okay, so how do we say this is self-balanced? Actually the in an AVL tree, the height so the concept of AVL tree is that, so for every internal node, okay, so let me go back. For every internal node, the height of the child of V differed at most by 1. So what does this mean? Okay, so let me explain. Okay. So here the difference, so this one is differ. Okay, so what is the difference between the height of these tuners, right? So the left side, so actually the terms, okay, let me go to the next slide actually, so we can explain better. Okay, so it is called balance condition. Okay, this is called balance condition, balance factor. In some books it's a balance factor. That means the balance factor in an AVL tree differs. Okay, it can be differ by at most 1. The balance factor, we can say balance factor balance factor can be either -1 or 0 or 1. Okay, so balance factor equal to, so you can say BF, or balance factor equal to height, so can say height of the left subtree minus height of the right subtree. Okay. So then, and balance factor must be either -1, 0, or 1. Okay, so we know that the height is always positive, right? So this is why it says differ at most by 1. So that is say -1 on 0 or 1. So we need to take, if we take absolute, then it is either 0 or 1, right? So here let us calculate the balance factor for some nodes. For instance, for this one, what is the balance factor? It is 0. So the height of this is 0, and then on the right side is 0. So 0 minus 0 equal to 0, right? So 0 minus 0 equal to 0. Okay, and here for this one, what will be the balance factor here? This side is 0, length is this side is 0, right? And here right side is 1. So 0, so 0 minus 1 equal to -1, right? And then for this one, is balance factor equal to this one balance factor 0, this one balance factor 0, and this one balance factor will be 0 minus 0, so balance factor will be 0. And for this one, balance factor is 0, and for this node balance factor will be 2. This side is length is 2, right? 2 minus, okay, 1. So it should be 2 minus 1 equal to 1. Okay, and for this one is balance factor will be this side is height 1, so then 1 minus this side is height is so this side height is 2, right? So there's 2, and then right side height is 1, 2, and 3. 2 minus 3 equal to 1. Okay, so you see that the balance factor is either 0 or -1 or 1. It cannot be 2, it cannot be -2. Okay, so for the balance factor balance condition, for every node in a tree is that is the height of the left subtree minus the height of the right subtree, it must be -1, 1, or 0. Okay, so now let us see which is an AVL tree. Okay, so how do we find that? How do we check that this is an AVL tree or not? Okay, so we will find balance factor, right? For this one balance factor is equal to 0, for this one balance factor equal to 0, for this one balance factor equal to 0, right? For this one balance factor will be 1 minus 0, the right side at 0, right? So that balance factor will be here, I'm sorry, 1 minus 0 equal to 0. For this one balance, for this one, this node balance factor will be what? This side is negative, this side 1, and this side is 2. 1 minus 2 equal to -1. Okay, for this node balance factor will be 1 minus 0. 1 minus 0 equal to 1. And for this one balance factor will be, so then what is the height this side of this left subtree? We will take the maximum path. Okay, so then 1, 2, and 3. 3 minus, and this side is 1 and 2. This side is equal to 3 minus 2 equal to 1. So for every node we see that it has balance factor 1, it has balance factor -1, it has balance factor 0, it has 0, it is I'm sorry, this would be 1. This is 1, this is 0, and this is 1. So either -1, So balance factor is the -1 or 0 or 1. So balance factor equal to here. So this is, yes, this is an AVL tree. Yes, AVL tree. Yes. Yes, tree. Okay, how about the right side one? Okay, then let us see that whether it is an AVL tree or not. So this balance factor is 0, this balance factor is 0, this balance factor is 0, this balance factor is 0. So all leaf node has balance factor 0, we can say. Okay, so then how about this one? So this is left side is height is 1, right side height is 1. So 1 minus 1, it will be 0. Okay, and for this one, left side is 1, and then minus right side is 2 equal to -1, right? It is okay. For this one, what is the height for this one? 1 2 3. So 3, and then on the right side, what is the height? 1. 3 minus 1 equal to 2. So it is not, this is not an AVL tree. Okay, for any given tree we can check that whether it is an AVL tree or not, and by checking that, what we can tell that whether this is a balanced tree or not. Okay, okay, so now, so in order to insert and remove an element in an AVL tree, there are some condition, balancing condition. Actually we need to check, always we need to make the AVL tree balanced. Okay, so this is why there are 4 kinds of rotations. I will briefly discuss about some rotation. Okay, so here, so we just saw that in an AVL tree is a self-balancing tree, and then that will ensure pretty log n with base 2 searching, right? But okay, developing an AVL tree is little bit difficult than building a BST. So actually, what is the problem? That at every stage, when we insert an element in an AVL tree, or you remove an element from an AVL tree, we need to check balance condition, balance factor for all nodes. Okay, and that is the complexity. Okay, so actually that's the difficulty. And when you resolve that difficulty when we design an AVL tree, then it will be pretty good and nice and efficient data structure for searching with log n time, right? So in this lecture, actually I'm not discussing detail about AVL trees. So what I want to do, so let us give some example about the rotation. There are actually 4 kinds of rotations in an AVL tree. Okay, that rotation is needed when we insert and delete an element from an AVL tree. Okay, For instance, let me come with a short one. Okay, this one. For instance, if we are given a data set with three simple data set, value 3, 2 and 1, okay, and we want to build an AVL tree. Okay, so how do we build an AVL tree? Okay, so 3 is comes first, so 3 will be a root element, right? 3 will be root element. Then 2 comes next, and 2 is less than 3, so 2 will be the left child. Okay, and here at this point it is fine, right? So at every point we need to check, for whenever we insert every element we need to check the balance factor. That means the balance factor, we know that balance factor must be either -1 or 0 or 1, nothing else, right? So here when we insert 3, the balance factor is 3, 0, right? There is no issue. When we insert 2, then balance factor for these 2 will be 0, and then 1 will be this 3, balance factor will be 1, left side 1 minus 0, right side is 0, that means it is 1, and then it's okay, right? Now when we insert 1, then 1 is less than 2, so 1 will go left side, right? And then balance factor will be checked, and we need to the balance factor will be changed, and we need to recheck the balance factor every time. So here this balance factor is 0, right? And then this balance factor is 1 minus 0 equal to 1, right? So how do we find balance factor? The height of the left subtree minus the height of the right subtree. And then what is the balance factor for this one? Height of the left subtree is 2, and so in this case the balance factor will be changed here, right? So balance factor will be changed over here. So what will be the new balance factor here? Okay, so this will be 2 minus 0, so balance factor will be 2. Okay, so this is not an AVL tree, right? So we know that in an AVL tree balance factor must be -1 or 0 or 1. So in this case this node has balance factor 2. So what do we need to do? We need to rotate it. Okay, we need to rotate it to make it an AVL tree. How do we rotate it? So there are 4 kinds of rotation. Number 1 rotation, we see that here the left and left, right? The child are left and left. Okay, child are left and left. So the rule of thumb is that, for instance, is the child are left and left. So then what you will see? So then you will do for this one. So you will do for left and left, you will do a right rotation. Okay, now rotation 1 rule is that for left we will consider only 2. Okay, only 2, the 3 adjacent nodes, and only 2 of the edges. Left do, okay, right do a, right actually do a single right rotation. only one rotation, single right rotation. How do the single right rotation? So this just these three will, let me change the color. Okay, these three will come down. Okay, these three will come down. So these three will come down. Think about it that the string, these are string, okay, and these are string, and this is there's a nail over here string. So then this will come. So that what will happen is, whenever you right rotation, then 2 will be so right rotation, 2 will be new root, and 1 will be on left side and 3 will go to the right side. Okay, so then now check the balance factor. So this balance factor is 0, this balance factor is 0, and this balance factor is 1 minus 1, this is also 1 minus 1, this balance factor is 0. So then it is an AVL tree, right? So now if we want to add 4 to 7, 4, 5, 6, 7 sequentially, what will happen? Okay, let us see. Okay, now 4, whenever it comes for 4, then inserting 4, since 4 is greater than 3, so it will go to the right side, right? And every time we need to check, whenever we insert, every time we need to check balance factor. This balance factor is 0, this balance factor is left side is 1, and the right side left side is 0, and length height 0, right side 1. So this balance factor will be 0 minus 1, 0 minus 1, this will be negative 1, and this balance factor will be 1, this balance factor 0, and this balance factor will be 1 minus 1, this is right side length 2, equal to negative 1. Okay, so then it is good. So this is good, this is good, this is good, this is good. So this is an AVL tree. Okay, now when we insert 5, so when we insert 5, what will happen? 5 is greater than 4, so it will go on the right side, but we need to check its balance factor again. So this balance factor is 0, and this balance factor is 0 minus 1, this is negative 1, so 0 minus 1, right? So this is negative 1, and then this is 0 minus 2, it is negative 2. Okay, this fails, and this is 1 minus 1, 2, 3, right? So this is 0, and this is 1 minus 1, 2, 3 equal to negative 2. Actually, what is good thing is that whenever we find an imbalance or illegal balance factor, then we don't need to go up, we just will consider only this adjacent three nodes to check or redo the balance factor here. Okay, redo the balance factor adjustment. So how do we do? For instance, this time you can see this is right and this is right and right. So if we have right and right, remember that if we have right and right, so this is rule 2, I can say rule 2 for right and right. We will not see up top, only we will see the 3. Right and right, do a single left rotation. So how do we do that single? Only this, for these 3, do a single lip rotation. For instance, think about there is this, these are string, this is a string, and there is a nail, this node is nailed over here. So then if we do a left rotation over here, so what will happen? 3 will go down, and then 4 will come here, and then 5 will come here. So that is this thing. Okay, this is the thing. So this part is left, single left rotation. Okay, and then now let us check the balance factor. For this one balance factor 0, this one balance factor 0. For this one balance factor 1 minus 1 is balance factor 0. For this one balance factor 0. For this one balance factor is 1 minus 2. 1 minus 2 equal to negative 1. Then it is okay. Then this is a this is an AVL tree, right? Okay, now we want to insert 6. Okay, now we want to see how do we insert 6. So then when we want to insert 6, what will happen? The 6, okay, these two are important. Okay, 6 and 7, this is a good example over here. Please remember that. So we will get our rule 3. Okay, now we will get our rule 3. So what is rule 3 over here? Now when we insert 6, right, then 6 is greater than 5, so then it will go to the right side of 5, right? So then at this point let us check the balance factor of each node. So this has balance factor 0, this has balance factor 0, this has balance factor 0, and this has balance factor 1 minus 1, that is, sorry, 0 minus 1. This next left side is 0, right? So that's with 0 minus 1 equal to negative 1, negative 1. For this one balance factor negative 1, and for this one balance factor will be, for this one balance factor will be 1 minus 2. So this one balance factor will be 1 minus 2 equal to negative 1. Okay, and for this one balance factor will be 1 minus 1, 2, 3. Okay, for height we will take the maximum height. Okay, maximum height. So there's 1 minus 1, 2, 3, right, equal to negative 2. Okay, that means this is an imbalanced BST. Imbalance, that means actually it is not an AVL tree, right? So then what is the problem? Problem is here, right? Problem is here. Okay, in this node. So then what we will do? Okay, so we will okay, so here in this case, that so this node will be in balance, and so then as it becomes imbalanced, so what we need to do, so we need to rotate, we need to consider the right wings of actually this. So this imbalance comes due to this node, right, this node, and this node, right? So then what will happen? So there will be rotation. Actually this is actually two and difficult, two rotations, double rotations. So then 4 will go to the top. You will see the 4 will go to the top, and then this will go down, this will go down, 2 will go down here, and then 1 will be on the left side, and then so this 4 is on the this. How about the other parts of 4? This. So then this side is on the right, so this will be on the right side of 4, this side on the right side of 4, and this side, this 3 is on the left of 4, right? So that means it will go on the left side of the root 4. So So the left side of the 4, what is the place that is available? So the left side of the 4, this one will be as is, this one will be as is on the left side, and then we see that only we have one position available, that was empty at the right side of 2. So these 3 will come to the right side of 2. Why it is right side of 2? It is right side of 2, but still you see that it is left side of 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 4, right? Here originally it was left side of 4, left side of 4, and then here in the rotated AVF AVL, it is also in the left side of the of 4. So okay, so this is a tricky part, but if you remember that one thing, that uh, that if it is in left side, so then on the of a subtree, then in the movement, after the movement, it will be in the left side. So still it is in the left side. So left side, this is the left side, okay, in the left side, but it will have its one will be in position, and then there is only one place remaining to go for 3, so the 3 will go right side. Okay, now similarly, actually okay, I wanted to write a formula for the left rotation, and then formula 3 and 4. I'm coming formula 3 and 4 separately actually with another example, so but let me finish this one. So how about inserting 7? So 7 is greater than 6, right? It will go on the right side, and then we need to check for every time we do an insertion, we need to check for balance factor. This balance factor is 0, this balance factor is 0 minus 1, that is negative 1, this balance factor is 0, this balance factor is 0, this balance factor is 1 minus 1, 0, and this balance factor is 0 minus 2, 0 minus 2 equal to negative 2, right? Negative 2, and this balance factor is 1, 2, 2 minus 1, 2, 3. So 2 minus 3 equal to negative 1. So we see that this balance factor is good, so there is no problem over here. So this is good, this is good, this is good, this is good, but problem is here, right? So as soon as we get a problem, we do not need to check for all other remaining nodes. Okay, so whenever we get an issue in our balance factor, we need to do right away with that. Okay, starting with that node to the next 2 nodes. Okay, so what are the next 2 nodes? It will be the last one that is added. So that issue arises due to the add of 7, right? So we need to consider only these 5, 6 and 7, these 3 nodes, and if we see that this is right rotation, this is right, so as we learned previously, that if there is a right and right, so then what do we need to do? We need to do left rotation, right? So in our previous formula we wrote that for right we need to do a left rotation, so that means 6, so we do a left rotation, that means 5 will be hanging here, and then 6 will be is root node, and then 5 will be here, and 7 will be on the right side. So now balance factor is 0, 0, 0, 0, and this unbalance factor 0, this unbalance factor 0, and this unbalance factor is also 0. So now it is an AVL tree. Okay, now okay, so now let me teach you a nice technique for nice techniques for double rotations. Okay, and then there are two double other rotations that I wanted to tell you. Actually, that let me recap it again first. So this one, for this one, this one is left, right? So left, so according to rule 1, what did we do? So for left, for left, do a single right rotation, right rotation. So what did you do? We did a single right rotation and we got this one, right? Okay, now and the rule 2, we learned that for right, so do a single left rotation. Okay, now rule 3, what will happen for a left right rotation? Okay, for left right, do need double rotation. Okay, and how do we do that kind of double rotation? That is a tricky thing, and then I want to give you a nice and intuitive technique so that you remember this forever. Okay, and then you never forget it. Okay, so for instance, let me give this describe this formula 2, 3 and 4 with something in general, not for this kind of. Okay, so for instance, if we have a node like A, okay, ABC, let's see, and then we want to we have node A, and then we want to insert another node B. So B, for instance, it is value, another value is less than B. Okay, so the left side is goes B. Okay, so and then we want to another value, for instance C. Okay, that goes right side. So here the left rotation, so here is left and right rotation, right? This is left and this is right, and this rotation factor is 0, and this rotation factor is 0 minus 1, so then it will be -1, and it will be 1 and 2, 2 minus 0, then it will be rotation factor equal to 2 minus 0, that will be rotation factor is here 2. So this is not an AVL tree, right? So then how do we make it an AVL tree? The technique is that for left right, so what do we find over here? So we got this and this, right? So then do this one, after the to go up and then go right. It is you can remember this, right? So for we already have here left, right, and then now do up and right. So okay, so instead of doing a double notation, so then do what do you to do? So do a single, okay, means up and R means right rotation. So then what will be going over here, see that. So then C will go to A, position A, okay, so on the top. So then it will come, C will come over here. So then C will come over here, and then B will be as is position, and then A will come here. Okay, then I wish I could give a different color for this. So do a single so let me delete this. Do a single UR rotation. So this is my technique. So you may not get it in a book, but it is double rotation. It's needed double rotation, but my technique is to do a single upright. So that means up here it is going C or down over here. So then C is going up, and then A is going over here right, and B will be in its position. Then what will be our AVL is this. Let us check now. Balance factor, this balance factor is 0, this balance factor is 0, and this balance factor is 0. So now it is an AVL tree, right? So now the similar technique, let us apply the similar technique for now rule 4 for right left. Do a single up left rotation. Let us give an example. For instance, example I can put over here. If I have A node over here, and then it has another node, for instance B over here, okay, and C over here. So this balance factor is 0, this balance factor is 1 minus 0, 1 minus 0 equal to 1, and this balance factor is 0. This side, left side is 0, and right side is length, height is 2, right? So 0 minus 2 equal to negative 2, right? So this is imbalance. So then what do we need to do? So then follow my technique. I believe you like it. So go up, okay, and then what was my original? My original was right and left, right? So then go up and left, okay, then up and left. C will go up and then left, okay, up and left. So up and left, that means C will go up, okay, from bottom to up. The C was the last element, so because the problem occurred due to the insertion of C, right? So C will go up, and then B will be in its own position, and then A will go left. This will be so A. Now you got A, C and B. You see that this is a binary BST, right? And then this will be a BST, and its balance factor is 0, its balance factor is 0, its balance factor is 0. Now it is an AVL tree. Okay, so this is the technique, this is my technique, so you can remember this way, by this way. Okay, so understanding array should be fine, right? So remembering array, because you are going up, why you cannot go right? Because the right lane is already, right side is already blocked, right? So it is an AVL tree is a binary search tree, and you cannot override, so then you have only the left child blank, so then you come left. Okay, and I hope you will remember this forever. Okay, so then if you remember this forever, so then for another technique for now, the last one, so in this slide, so the slide is pretty large, so we do not need more. So whenever you see that there are some maybe here some insertion, if due to some insertion, for instance 14, if an occurrence of imbalance happen, that you need to consider the previous rule. For instance, if for at any position, let us check what is the position, what is the problem occur over here, right? So this balance factor is 0, this balance factor is 0 minus 1, that is negative 1, this balance factor is 0, and this balance factor is 2. This side is 2 minus 1, that is 1, and this balance factor is 0, this is 0, this is 0, and this balance factor is 1 minus 1 2 3. So then 1 minus 3, so this balance factor is negative 2. So the problem occurs here, right? The problem occurs here, the problem is over here. So what do we need to do? We need to take these entire things. Okay, so here, so the problem is here, right? So now where the problem occurs, so due to the add of insertion of 14, right? So then wherever the problem occurred, we will take how can I tell you? Okay, we see that the problem occurred here. Sorry, I just okay, problem occurred here, side like over here. So this balance factor is 1 minus 1 2 3. So that means balance factor is negative 2. That is not allowed for an AVF. So what do we need to do over here? So starting from this node and the adjacent 3 nodes, adjacent 2 nodes, 1 and 2. So what is over here? So you remember that it is a right and left, right? So as we learned for rule 4, for a right and left, you can do an up, yeah, let me change the color, an up and down and left. Okay, up and left, right? So then up, that means 7 will go in the position of 6. You see that 7 will go in the position of 6, 7 will go here, and the 7 will go here. You see the 7 here, and then 6 and 5 will come down, and 6 and 5 will come down, and that 7 has this position, this position is empty, right? Then 14 will go over there, and then 14 will take the position of 7. So then if you remember this one for the rule 4, recall rule 4. Okay, for the rule 4, technique for a right left, you can do a single, what is that called, up and left rotation. Then if you follow this, this is the buck, this is here. So what the technique is that, don't be misled, wherever we get an issue, so this is the node we got an issue, right? Okay, and what is the issue coming from? The issue is coming from due to add of 14. So starting from this node, we will go towards 14 and we will take only 3. We will take only 3. Okay, so the 3 nodes. So we will take only 3. We will go towards 14 and we will take, we can say only 2 edges, right? So this is right and left, not else. We don't need to go over here. So as soon as you make balance over here, it will be balanced everywhere. Okay, so then what you will do, this 7, it will go up and this and left. Okay, up and left. So then now it will be balanced. Now we'll check the balance factor. This is 0 0 0 0 and 0. This is also 0 and this is 1 minus 0. This is 1, and now it is checked. 2 minus, this side is 2 and this minus side is 2. 2 minus 2, it is 0. So then it is okay, right? Now it is an AVL tree. So now on the left side we don't need to check. So this is 1, sorry, 1 minus 1, then 1 minus 1, this is 0, is balance factor is 0, and then here there's 2 minus 1 2 3, 2 minus 3 equal to negative 1. Actually we do not need to check it actually, so we just fix this one and everything will be fixed, right? So the two techniques actually, technique technique 4 and 3. Okay, if you follow this, actually there are 4 rotations technique. If you follow this, then you will be able to build any AVL tree, okay, or check whether a tree is an AVL tree. And by doing this, actually we will need this AVL tree for our next discussion about what is that called, red black tree, that we'll discuss in our next lecture. Actually in this course, actually again I'm telling that we are discussing the we are analyzing the algorithm, not we are implementing an algorithm and a data structure. Okay, so there are codes over here, so you can get code for implementing AVL tree. So this is not part of this course actually. Okay, and please remember this, mainly the I wanted to teach you what is an AVL tree and what are the benefits of an AVL tree and how the AVL tree is built and what are the 4 kind of rotations for an AVL tree. Okay, and thank you so much, and I think you will remember this forever. Okay, thank you so much. I will see you in next